Mathematics is constructed from other math, which is constructed from other math, and so on. But what happens at the bottom? What grounds all of mathematics? Or is it just turtles all the way down? Mathematics is cumulative. It builds on itself. That's part of why you take math courses in a fairly prescribed order. To learn about matrices, big blocks of numbers, and the procedure for multiplying matrices, you need to know about numbers. Matrices are defined in terms of, in other words, constructed from, more fundamental objects, numbers. For this reason, it's not uncommon for people to view mathematics as a giant pyramid, with objects and concepts constructed from things below them. Let's pick as a concrete example 4 different types of numbers: real numbers, rational numbers, integers, and natural numbers. Remember that the natural numbers are all the counting numbers, usually taken to include 0, so 0, 1, 2, 3, 4, and so on. Building up the pyramid from the natural numbers, we can define the integers as being the result of subtracting natural numbers. They're all the possible things you can get by subtracting one natural number from another. So 3 is an integer because it's 3 minus 0, and negative 3 is an integer because it's 0 minus 3. More precisely, we can define each integer as an equivalence class, or a particular collection of pairs of natural numbers. For example, the integer 3 is the collection 30, 41, 103, 100, and so on. And the integer negative 3 is the collection 03, 14, 100, 103, and so on. Under this definition, the integers also inherit their structure and properties from the natural numbers. For example, the integer associated with xy is less than or equal to the integer associated with zw if x plus w is less than or equal to z plus y. The order on the integers is defined using the order on the natural numbers. And the integer associated with xy plus the integer associated with zw is equal to the integer associated with x plus z, y plus w. Integer addition is defined using natural number addition. You should check that this structure aligns with your intuition about the integers. We've constructed the integers using the natural numbers, and then from the integers we can build the rational numbers. They're all the possible things you can get by dividing one integer by another, like 1/2, 7 over 512, or negative 3 divided by 1. And similar to the previous construction of the integers, we can define the properties of the rational numbers in terms of the properties of the integers. One step further, we can also construct the real numbers from the rationals. But it's a bit more tricky, using something called a Dedekind cut. A Dedekind cut splits the rational numbers into 2 sets. One set is made up of all the rational numbers below the cut, and the other set is made up of all the rational numbers above or at the cut. Let's make the cut here. All the rational numbers less than 3 are in one set, and all the rational numbers greater than or equal to 3 are in another set. This cut, or way of splitting the rationals, is identified with the smallest rational number in the upper set, which is 3. The cut defines the real number 3. Notice that the lower set doesn't have a biggest element. There is no rational number immediately below 3. For any rational number below 3, for example 2.9, there will always be another rational number between that and 3, like 2.95. Let's define a new cut. The lower set is all the rational numbers x, such that x squared is less than 2, and the upper set is all the rational numbers y, such that y squared is greater than or equal to 2. In this case, there is no smallest element in the upper set. It would be the square root of 2, but that's not rational. This Dedekind cut defines the number square root of 2. This particular way to split the rational numbers can be thought of as the definition of the real number square root of 2. The real numbers are defined as all the possible ways to cut or split the rational numbers. The cut is identified with either the smallest element in the upper set, if one exists, like 3, and otherwise it's the gap between the two sets, like the square root of 2. Starting with the natural numbers, we subtracted them in all possible ways to get the integers. Then we divided the integers in all possible ways to get the rationals. Then we split the rationals in all possible ways to get the real numbers. The structure and properties of each type of number can be defined in terms of the previous type. In this way, all possible statements about the real numbers, like pi is less than e squared, can be reduced to statements about natural numbers. Mathematical objects and their properties, the things we prove theorems about, are defined in terms of other mathematical objects and their properties. Math is built out of simpler math, hence the pyramid idea. But where does this process of simplification end? In other words, what holds up the bottom of the pyramid? In the late 1800s and early 1900s, this was a real crisis for mathematicians and philosophers. Mathematics has no foundation. Gottlob Frege and Bertrand Russell were very worried about mathematics' seeming lack of a foundation. Along with Richard Dedekind of the aforementioned Dedekind Cuts, they founded and advocated for a philosophical position known as logicism, as in logic plus ism. Basically, logicism says that the bottom of the pyramid of mathematics is logic. Mathematics is founded in logic. Essentially, mathematics is logic. In Russell's words, the goal of logicism is to show that all pure mathematics follows from purely logical premises and uses only concepts definable in logical terms. Just as we reduced all statements about the real numbers to statements about natural numbers, the logicist wants to reduce the natural numbers, and everything else, to logic. This leads to some obvious questions, like, what exactly is logic? Logicism is a philosophical position, and the intended meaning of the word logic is fundamentally philosophical and not mathematical. The definition is difficult to pinpoint and different for each logicist. But mathematician Ernst Snapper writes that generally, the logicist thought that a logical proposition is a proposition which has complete generality and is true in virtue of its form rather than its content. For example, the law of excluded middle. For any proposition P, either P or not P. Logic should feel simple, natural, and never ad hoc. That's what allows it to ground mathematics, to sit at the base of the pyramid. In the late 1800s, Gottlob Frege became the first person to earnestly attempt to carry out the logicist project. He spent years developing an extensive system of logical axioms and notation, a foundational system from which he derived the basic laws of arithmetic. The project seemed to be a logicist success until Bertrand Russell rather famously ruined it. Just as Frege's book was going to press, Russell pointed out that Frege's system contained a contradiction. Using the basic law 5, one could derive Russell's paradox, the set of all sets that do not contain themselves. Even though Russell witnessed the specific errors in Frege's work, he was inspired by its central goal, to give mathematics a logical foundation. Together with Alfred North Whitehead, Russell continued to push the logicist agenda in their 3-volume Principia Mathematica. The work succeeded in reducing large sections of mathematics to an axiomatic system, and famously exhausted the first few hundred pages proving that 1 + 1 = 2. But not all the axioms they used were pure logic. This is essentially the same status as mathematics' most well-known axiomatic system, Zermelo-Fraenkel set theory. From the axioms of ZF set theory, even without the sometimes controversial axiom of choice, one can derive most of classical mathematics. That is, you can reduce most known math to those 8 or 9 axioms. A logicist success. We now know, thanks to Gödel, that we'll never have an axiom system which produces all of math. It's impossible to prove the ZF axioms will never produce a contradiction, but none have been found so far. Another good sign. Unfortunately, some of the ZF axioms cannot be considered pure logic. For example, the axiom of infinity, which asserts that there exists infinite sets, cannot reasonably be considered an axiom of pure form. It asserts something about content, something more than basic logic. So, as Snapper jokes, since at least 2 out of the 9 axioms of ZF are not logical propositions in the sense of logicism, it is fair to say that this school failed by about 20% in its efforts to give mathematics a firm foundation. Logicism had some successes, and huge portions of modern mathematical logic are the historical or mathematical consequences of the crisis about the foundations of mathematics. We've never really figured out what's at the bottom of the pyramid, but along the way we've discovered a ton of other fascinating mathematics and philosophy. Hello! You all had a lot of awesome responses to our episode on pseudo-random numbers, and a lot of your comments had to do